Okay, I think we can get us started. Hello, everyone. Welcome to the first CIIR talk of the spring semester. It's my pleasure to introduce Professor Danqi Chen from Princeton University. She's an assistant professor and co-director of the Princeton NLP group. She also serves as the associate director of the Princeton Language and Intelligence. She works on various aspects of large language models, especially making them useful, available for academic communities. And before joining Princeton, then she has been part of the FAIR, Facebook AI research. She received her PhD in 2018 from Stanford with Chris Manning. And before that, she received her bachelor's degree in computer science from Tsinghua University in China. Her work has been received multiple awards, a lot of recognitions, and they include a Sloan Fellowship, an NSF CIIR Award, a Samsung AI Researcher of the Year Award, and multiple outstanding paper awards from ACL and EMNLP. Today, she'll talk about RAG and long context large language models. And I think without further ado, please welcome Danqi virtually to UMass.
Okay, thank you. Thank you for the kind introduction. Today, I'm excited to be here and to speak with all of you. So I know that I put RAG and the long context models in this talk title, but this talk will be really mostly about long context model. So some of you may have know that I've been actually working on retrieval-augmented language models for quite a few years. So the more I think about the problems in RAG and the problems in long context models, the more actually I see a natural synergy between the two. And hopefully I can touch upon a bit in this talk today. So today my plan to actually share a couple of projects we have worked on in long context models over the past 1 or 2 years. And more importantly, I would like to share some insights and even a few beta lessons we have learned when we developed these projects. So the work I'm going to discuss today has really been led by a group of amazing postdocs and students. I would like to actually all acknowledge them at the beginning. So this includes like my student Tianyu Gao, Howard Yan, Alex Vetic, and our postdoc Xi Ye, and many others. So why do we care about long context models? So people are excited about them because they can really support a wide range of the real-world applications. For example, we can use language model to answer questions or summarize information from a research paper. For example, you can just upload the GPT-4 paper to ChatGPT and ask the model to give you a summary. And we can also ask basically build language agents to perform the repo-level code understanding or process large amounts of web content. And the RAG is actually also a very important application that actually benefits from the long context capabilities, as it actually requires integrating documents from like multiple retrieved sources into this generation process. So how long do I mean by long context models? So just to give you some perspectives here, if we look at GPT-3 paper, it actually has 75,000 tokens, I believe, based measured by Llama tokens. And the entire Dune book series has around 1 million words. And the transformer package has about like 10 million tokens. And then if we think about like a RAG application, let's say we take 100 web pages, they are basically roughly can count as like 100,000 tokens. So here is actually a fun fact. And I was actually pretty surprised by this when I worked on this slide. So back in basically mid-2023 was just about 1.5 years ago. So we really didn't have models that can support very long context sizes. At that time, Llama 1 has a 2,000 context window size, and Llama 2 has 4,000 context size. And even GPT-4 at the time could handle at most 8,000 context tokens. Today, you probably all have heard of this kind of recent advances, like Llama 3.1 and the GPT-4, all this support like 128,000. And the Claude 3.5 has 200,000 tokens, and the Gemini basically they claim they can actually support like a 2 million context window size. To me, it's actually very hard to believe how much progress has actually happened in just this past year. So as an academic working on like these related problems, we actually have learned a lot along this way. So next, I want to talk a little bit about why I actually become really interested in long context models. So actually, basically in early 2023, we had this project called ALCE, so which stands for Automatic Large Language Models Citation Evaluation. So you're probably all familiar with this kind of citations if you have used a commercial system like Perplexity. Basically, ALCE is in this ALCE project, we propose an end-to-end automatic evaluation framework for such a citation task. So the task basically works as follows. Given an input query, like when did the US break away from England? And we ask the system to first retrieve a set of passages from like a large collection of documents, and then generate like accurate and coherent output with proper citations. As you can see from this example here, so at the end of each individual like statement sentence that it generates, it has these like numbers like 1, 2, 3 that actually referring to the passages the system actually retrieved. So I will not go into details of this work, but in order to develop these benchmarks, and at the time we test the best language models available at the time, this early 2023. Actually, Llama 2 even came out after we almost wrap up this project. So we basically tested like Llama 1, Llama 2, and the GPT-4, and also some instruction tuned models based on Llama like Alpaca, Vicuna. Again, the context size window basically range from like 2,000 tokens to 8,000 tokens. And this is what we actually learned from this ALCE project. So the figure you can see here is actually based on Llama 3. My student regenerated this figure, but the story is basically the same. So the left figure, as you can see from this slide, is based on metrics based on the correctness. And the figure on the right is based on the citation quality. And there is actually like a green curve here. Basically, we call it retrieval recall. It basically serves as an upper bound to see like basically how much correct information that has been already included in the basic top K passages. And what we learned here is the performance, even if we can put all these kind of retrieved passages in the context window, that's only 4,000 to 8,000 context window size at most. The performance still degrades a lot with the increasing number of the documents. Like correctness, basically like you see the performance starts to decrease after 20 documents. But for harder tasks like citation, the performance basically starts to decrease immediately after basically 5 documents. That really means that the models, the current set of models, language models, are not really able to leverage this kind of retrieved information in the context information. And another key finding I don't see show in this figure is we also find the instruction following is actually very important for solving such citation tasks. And in this talk, I would like to discuss more about this kind of balance between the long context capabilities and also the strong instruction following. Okay, so this basically the motivation for why I started to work on like long context models. Clearly, at the time, we actually need better long context models. So we need to figure out how to really expand the context window size of the language models. If they only have like 2,000, 4,000 context size, they just cannot support a lot of useful applications. And more importantly, we need to figure out how to make these models actually better leverage context and also can do better instruction following. But in order to develop long context models, the first question we actually want to ask is what evaluations should we actually trust? So ALCE is actually a benchmark we already developed at that time. But ALCE is actually still a pretty complex and a difficult task. And we can also think about using Perplexity to basically develop long context models. Or maybe we should think about other downstream tasks. So next, I would like to talk more about how we should even evaluate long context models. So let's first take a look at how long context models are actually evaluated in our research community. So to my surprise, actually there are dozens of papers that basically simply rely on such a task called needle in a haystack. So you probably all have seen this kind of green, red, grid figures like the one I showed here. So needle in a haystack is basically a very simple task. It's try to insert a needle into a large amount of irrelevant text, and then ask a question about this basically insert needle. For example, what is this special magic number mentioned in the text? There are also some other improved versions like NVIDIA's this ruler benchmark, which essentially tries to introduce some hard distracting text to make this retrieval problem more difficult. But at the end of this day, these tasks are still highly synthetic. It's actually not very clear how this task can actually well transfer to the real-world applications. The good thing about this synthetic task, or needle-in-haystack task, is that this task actually very easy to test. And they can give developers like full control over like how long the input length you actually want to test and where you actually want to insert the needles. So on the other end of the spectrum, there are also a lot of evaluation benchmarks that try to focus on downstream tasks. I'll just list a bunch of the benchmarks here in the space, including like zero scrolls or long bench or infinity bench and many others. So these benchmarks primarily evaluate the real-world tasks like question answering or summarization over books or the meeting transcripts. So here is basically like a figure I took from the scrolls benchmark. But there's still like several critical issues remaining. So the first issue here is that for all these kind of real-world benchmarks, you actually don't really have control over the input length or even where the critical information is actually included in this long context input. And also another bigger problem is that most of the existing data sets, they actually really don't have very long input. Most of the input lengths have actually less than 10,000 input tokens. And the second problem here is because the question answering and summarization, some of these tasks are actually pretty challenging. They actually really require me to actually develop instruction-tuned models to actually solve these problems. But still, at the time, most long context language models focus on the base models instead of the instruction-tuned models. And the third problem we actually discovered during basically our model development process is we actually find the evaluation metrics used in many of these benchmarks are still based on very simple stream match metrics, such as root for summarization. There has been actually a lot of papers already show that using this kind of stream match evaluation in this large language model area is actually really has proved to be highly unreliable. Okay, so the last metric I want to talk about is actually perplexity. Actually, around 2023, there are still a lot of papers, especially focusing on how to extend the long context window. They basically primarily use perplexity as their evaluation metric. So here, I actually just want to simply claim that perplexity is just really not a good indicator of the downstream task performance for long context models. So the figure I've put here is actually from a paper that I will talk about later. Basically, we show that perplexity is just not a reliable metric for making some important design choices, such as data mixing. And actually, only pretty recently, we actually come across this paper, actually the CIIR 2025 paper, that actually addressed this issue actually more systematically. So this paper is titled as "What's Wrong with Perplexity for Long Context Language Modeling?" There are actually findings basically just aligned with what we observed. There's basically no clear correlation between perplexity and also downstream task performance. So at this point, we decided, okay, there are so many different issues in the current evaluation and the benchmarks. So we decided, okay, why not we just build another reliable benchmark to guide us to actually develop long context models. So our initial goal was actually just try to figure out which set of tasks we should trust for our own internal use. But this actually eventually led to actually a big team effort. And we eventually actually led to a research paper that we are going to publish, will appear at CIIR 2025. So this benchmark is called HELMET, which stands for How to Evaluate Long Context Models Effectively and Thoroughly. And this project was led by my student, Howard Yin. So just to give you a quick idea of why we think HELMET is a better benchmark. So here's the figure, actually comparing the different types of frontier model at 128,000 evaluation context lengths. So existing benchmarks such as needle in a haystack is basically all saturated. All the accuracy are basically 100%, except for this like Gemini Pro. I don't know. I think there's an artifact here. The performance is very bad here. And also the and also some other benchmarks like Ruler and Infinity Bench. We found that actually often produce very inconsistent trends. For example, you can see that the performance of Llama 8 billion model is actually better than the performance of the Llama 70 billion model for both benchmarks. And also the Gemini Flash is actually better than Gemini Pro on the Ruler benchmarks. So we actually this kind of unexpected. So in contrast, we actually test these models using our own HELMET benchmark. At least the results are actually pretty much aligned with what we actually expected among these model rankings. So next, let me talk about what task actually the helmet actually includes. So the first question we want to ask here is, what long context capabilities do we actually really care about? Do we actually really want to test in this kind of real world like applications, and also when we want to deploy these long context models? So here are the abilities that we decided that, okay, these are important things we need to care about. This actually includes like recording needles. That's basically like needle in haystack. We actually want to identify the relevant information from the long context. So we care about the models to be able to actually reason over the very long document. And we want to make sure that the model is actually able to be robust to actually irrelevant context or noise. And then we also want to ensure that the models can actually learn new tasks from the context itself to learn the new tasks on the fly. And then finally, we care about the model's instruction following ability. So the second decision here is, do we actually want to include a synthetic task or real world task? So we decided, okay, we definitely need to test the real world task performance because we eventually want to use this model for the real world applications. So we decided to cover the following applications, including like non-documented question answering, summarization, and also RAG applications. And we also include this new task called passive re-ranking. I will explain in the next slide, and as well as the many shot in context learning. Finally, for our helmet benchmark, this is actually a very detailed point, but also actually a very important point that we put a lot of work here. That we actually want to make sure that the benchmark is actually very reliable in terms of both evaluation metrics and prompting. We want to make sure that the prompt will be not just sensitive with like a very detailed design choices. Okay, so this is what we end up deciding to include in the helmet benchmark. So the helmet, essentially, we include 7 different categories. So we still kept like a needle in haystack, or we call it synthetic recall task that cares that basically tests the synthetic test to measure where the basic needle is in the long context model. And we also include like 6 categories of the real world problem applications, including the RAG, passive re-ranking, many shot in context learning, long document QA, summarization, and finally is actually the citation benchmark. The ALCE benchmark I actually talked about at the beginning. So we care about both the correctness of the model output as well as the model's ability of doing the citations. So I should note that actually many of these tasks are actually highly controllable. That means that we can actually compare these different models at actually different input lengths. So we can actually easily extend the basically the different tasks at a different input length level. So let me give you some ideas about what we exactly test in this benchmark. So for RAG, essentially is the open domain QA task. So let's say the problem is use the given document to write a concise and short answer to the question, and write the answer in this answer format, and then followed by a set of documents, and then followed by the actual question we ask. So this is a question from the hot QA data set. Because the answer could be very short, so here we just need to use the exact match for the evaluation. And then for the passive ranking, the task is also very straightforward. Essentially, we put here like rank each document based on their relevance to the question in the descending order. Please output the final output in this format. Ranking ID3 is better than ID1, is better than ID2, and then followed by like a bunch of documents with the ID, and then followed by query, and then we expect model PhD to finally generate this like a ranking. And then for the many shot in context learning, it's actually a pretty standard task. It's like basically we put a bunch of demonstrations in the context, but it's many shots. So it's actually like we put like up to hundreds of the input instance in the context. But the important thing here I want to mention is that we actually don't use actually the real labels. For example, in this test classification problem, we decide to not use like sports or science. We decide to actually replace the real labels by this kind of abstract labels. So that actually means that we enforce the model to actually be able to learn from the context and actually learn to how to do this task. So here is basically the full table of our final helmet task. So here again, 7 categories, and each category covers like a bunch of the individual data sets. There are actually a lot of the detailed discussion in the paper about how we do prompting and evaluation, so feel free to check out the paper. So I just want to highlight a couple of things here. So the first thing here is For the long document QA and summarization, we actually picked only the data set that actually really require the long documents to actually do the QA or summarization. So the average length of this input length already basically 100,000 tokens. And also another very important thing here is that we decide to opt to model-based evaluation, basically using large language model judge to decide whether the output makes sense or like how good the model's output, instead of using like root metrics, those kind of simple heuristics to decide the final metrics. And then we found this actually very important. So for the many short in-context learning, we basically picked 5 tasks here. Most of the tasks are like classification tasks, but they actually have many labels. So that really means that we actually need a lot of the shots, or need a lot of demonstrations in the context to actually make sure the model can actually learn from the context to actually do the final task. Finally, we also include like a bunch of synthetic recall tasks, but we didn't include the orange or needle in haystack task. We actually select a bunch of really hard synthetic tasks here. And in the paper, we also analyze that this task can be actually better correlated with actually the real world downstream task. So here are actually like a kind of big table of kind of the results when we try to evaluate like many different long context models on helmet benchmark. There are actually more results in the paper. So just to highlight a couple of things here. So first, if you just look at synthetic recall, you can see that a lot of models can actually achieve very good performance, basically like almost like over 80, 90, or almost 100%. Even these are the hard synthetic recall tasks. So that really means that these tasks are good for like a sanity check, but it's really not good to really differentiate the strong long context models. RAG is a pretty reliable task, but still the numbers are generally pretty high and relatively easy for the frontier models. But when we look at a task like a citation or the passage ranking, so we found that there's a big like the open source models, the open weight models, lag behind the frontier models really by a very large margin. You can see what I highlighted here. Basically, all the numbers are really poor for citation tasks and the rank for this open source model. That means that there's still a lot of things we can do in the open source community. Okay, so finally, we also look at how these tasks are actually correlated. So just to highlight here, I think I have, okay, sorry, yeah, here. Okay, so yeah, so we actually find that the RAG is actually a pretty good downstream task. It actually correlated pretty well with other downstream tasks. For example, like passage ranking and the citation. And the in-context learning is actually a very different task. It's actually not correlated well with many other tasks. So in the paper, we finally conclude that we actually encourage the developers, if they want to some fast development, that we recommend them to use the synthetic recall RAG for the kind of first round iterations. And finally, we believe that all these different categories or different tasks actually represent very different long context capabilities. So we still advocate for like basically a holistic evaluation across a diverse task. So this is basically what I want to tell you about this helmet evaluation. And we're actually pretty happy that our helmet task and the category have been already picked up by the industry, especially this Microsoft 5.4 model has been already used a helmet in their long context evaluation. Okay, so I'm just going to end here. This is my first part. I will see if there are any questions before I move on to my next part. Yeah.
Any questions from the audience? Feel free to raise your virtual hand on Zoom if you have any questions. I think we can continue.
Yeah, I'm also happy to answer the question at the end. I have a lot of stuff to go through today. Yeah. Okay, so this is about the helmet. So we are pretty happy with helmet. We believe this provides a pretty reliable evaluation across like many different dimensions of the long context models. But still, most of the tasks on helmet focus on long input and the short output, for example, question answer and summarization. So next question I want to ask is, what about these models, the long form generation ability? So next, I want to introduce another evaluation benchmark. We actually did pretty recently called LongProc, benchmarking long context language models on long procedure generation. So before I talk about LongProc, I wanted to actually talk about reasoning models. This is probably currently the most popular research topic at this point. So we all know about these reasoning models, like O1 or the DeepSeek R1 models. So one important feature of these models, reasoning models, is their actual ability to generate a very long chain of thought. to solve very complex tasks such as mathematical problems. So I put one example here. The very long train of thought is just part of the output, and it has actually many different transitions such as wait, and alternatively, and so on. So I also put this recent paper found here, which actually demonstrates that a lot of reasoning models like DeepSeek R1 or QWQ, they actually usually need to generate 5,000 to 16,000 tokens on this AIME 2024 problems. So next, I would like to introduce our project called LongProc. So we actually started this project a couple months before we knew about O1 or R1 models. So we actually didn't know about anything about reasoning models at that time. But it's actually very interesting to think about the reasoning models in this context. So unlike Helmet, so when we developed, I should mention this. Yeah, so this is actually the LongProc paper we put on archive like in last month in January, and this project was led by postdoc CIIR, and also it's actually a big team effort. Also includes his PhD advisor, corrector, and many others here. Okay, so different from Helmet. So when we develop this benchmark, so there are actually really two desired properties that we actually want to feature in this benchmark. So one, we call it the high dispersion. So the high dispersion, that means that we actually really want to make sure the model to be able to actually integrate like a lot of the highly dispersed information that actually scattered at many different locations on the input. So instead of just retrieving like one or very few relevant snippets, we want the models to actually really gather information at many different places. So we took this term dispersion from this actually a very recent position paper called Towards Generally Difficult Long Context NLP. So which actually argues for the importance of dispersion if you want to build a really hard long context NLP task. So secondly is actually the long form generation. So we want to make sure the output should be actually long. So, but the challenge question here is that how can we evaluate long outputs, but still ensure like a reliable evaluation? There are already some other benchmarks on long form generation. So, for example, ask the model to just write like a research paper or like book chapter, but it's actually basically infeasible to evaluate the model's output. So here is basically our idea. So we propose to actually use the long procedural generation as a way to evaluate the long context model's ability for such generation tasks. So we actually require the model to actually, for all the tasks on this like a LongProc benchmark, we require the model to execute like a very detailed and a pre-specified procedure. So this actually really requires the ability of the instruction following. And then we ask the model to actually execute this procedure and then do the step-by-step generation. So at every single step, the generation needs to depend on the input and also all the previous generations. So this actually enforces the model to really has to integrate the information, the dispersed information actually across the different places. And some harder tasks in LongProc at every single individual step may actually also require reasoning. And the finally, we also want to make sure the models to be actually long, but also structured. So what I mean by structured means that the model really need to follow this specific procedure to actually really generate the answer step by step. So this actually gives us an advantage that we are able to actually do the reliable rule-based evaluation. And also another big advantage here is that we can actually make sure that we can control the output length. So we can actually design the task at an actually different difficulty level and also the output length level. So here are basically the 6 tasks we include in this like LongProc benchmark. As you can see here, we basically designed 3 levels of difficulty at the output length of 500 tokens, 2,000 tokens, and 8,000 tokens. And the 6 tasks that I'm going to talk about later. And all these different tasks actually also have like a different require different capabilities. So they're all required to access information from the input, but some require like just a sequential processing. Some actually require to find like targeted information. Some tasks actually require reasoning, and some other tasks require you actually need to do the search process to solve this task. So I don't think I will have time to really go through all the tasks, but I will show you a couple of tasks. I think I'm going to show you 4 tasks in the next couple of slides to give you an idea about what this task really mean in terms of long procedure generation. So the first task is called HTML to TSV. So this actually is really the most simple task we have in this benchmark. So essentially, the idea is that the input is basically an HTML page. It's a very long HTML page. And then we basically ask the instruction is like, for example, find the title, year, genre, and the rate of the movies, and listen in a TSV. So the model, basic task requires the model to process a very long input, and just try to sequentially process the information, and finally extract the relevant information and convert them into like basically a TSV format. So this doesn't really require reasoning, but it requires to execute this step, like processing like row by row, step by step, and the final output is also deterministic. This is a very easy task in LongProc. And then next, let's look at a more interesting task called theory of mind tracking. So here the idea is there's a story, and the story is about like a bunch of people and also a bunch of objects. So basically, we want the model to actually able to track the locations and where each person is at every single step, and where every single object is actually placed after every single step, and also like we want to ask like the person's belief about like where an object is actually placed at every single step. For example, at step 0, Alice in the bedroom, Bob in the bedroom. The pencil is on the Pedio's coffee table. The notebook is also on the coffee table. And then we start to take actions. And then finally, the question is, where does Alice believe the notebook is? And then to actually really execute this kind of theory of mind tracking, we ask the model to basically execute this procedure. And at every single step, it needs to output where Alice's location is, where the because the question is about Alice and where the notebook's location is, whether the Alice actually sees the notebook, and also where is Alice's belief on where the notebook is. So basically, step by step. Finally, we check whether the model is able to get every single step, all this kind of entire trajectory to be correct, and then finally give you the final answer where the Alice believes the notebook is. Okay, so next two tasks is actually the most challenging task. One task is called countdown. So this countdown task is basically, you can think about this as a generalized version of the game of 24. Basically like given a set of numbers, and also the basic arithmetic operations like plus, minus, and multiplication, division, and there's also a target number. And then we want the model to be able to compose all these kind of 4 numbers in this set and to reach the final target number. So we ask the model to basically follow this like a very specific procedure. So we basically use a depth first search, is a basic brute force search procedure to actually enumerate all the possible pairs in this like data set and try to compose 2 numbers, and then continue this search procedure until so you can see from the basically the figure on the right, until the finally the model is able to actually reach the target number 12. And the final solution is like, basically like 3 steps that you are able to figure out how to really compose all these numbers to get the final number. And then for the evaluation, because we found sometimes the model don't follow the exact search order, so we only care about the final solution. We only evaluate whether the final solution is correct or not. So this basically like has some reasonability. The model needs to figure out how to compose the numbers and how to validate the number, but also need to follow this kind of particular search procedure. And the last task here is also very similar. We call this task as travel planning. Basically, the idea is that we want the model to so I'll give the model, the task is basically I'll give you like a bunch of cities in, like, for example, in Europe. And I will tell you like which cities there are actually direct flights between. And I want to say, okay, I want to spend a couple of days in which city. I want to spend maybe 5 days in another city, and maybe between like day X to day Y, I want to visit another city. And then we finally want the model to come up with a travel plan that actually satisfy all the constraints. And very similar to countdown, basically we want the model to execute a depth first search procedure, basically like try to decide, okay, try to search what should be the next city to visit and how many days that this person should actually visit this city, and until to make sure, and also check whether the constraints have been already met until it actually reaches the final solution. Okay, so now you probably already get the idea, basically like what I mean by long procedure generation. You can also see that all these different tasks have different levels of difficulty. And also they're actually very easy to evaluate because all the output can be actually pretty deterministic. And actually can use rule-based evaluation metrics to check. Okay, next I'll just similar table as I showed on the helmet. I will just show you what the results we actually learned from like developing this benchmark. So the first thing we found is the open weight model, similarly, or like smaller open weight model, like Llama 3.1 8 billion model or Chen 2.5 7 billion model, they actually really perform poorly, even at the 500 token level for this very simple task. If you check like a theory of mind tracking or travel planning or like countdown, the smaller models can really perform very poorly on this like task, even at 500 token output length. Remember the like helmet task, the input length can be already like 128,000 or like at least 64,000. But for this like output, long form output, the 500 output length is already pretty hard for such tasks. Second, we found scale actually really matters. If you compare, let's say, Llama 3.1 to Llama 3.1, 8 billion to 70 billion model, actually the performance improved a lot actually across the board. So we believe actually scales actually matters a lot for all this kind of at least for all these LongProc tasks. Finally, we found that for some harder tasks like theory of mind tracking or travel planning, even the frontier models like Gemini 1.5 Pro or GPT-4o model, they still perform very badly, very bad at actually at 8,000 output length. So that means that there are still a lot of things we can think about how to improve even the current models. Okay, so the last point I want to talk about here is actually about this procedural thing. I want to go back to the point about the reasoning models. So I want to ask a question. So in all this LongProc data sets task, that we actually specify a very detailed procedure to ask the model to follow the procedure to actually solve this complex task. So is this procedure pre-specified procedure actually helpful or useful? So when we wrote the paper, we don't really have like R1 models yet. So at the time we still tested the GPT-4o model. So we basically compared the zero-shot chain of thought versus this kind of pre-specified chain of thought, like the procedural chain of thought. We found that definitely the pre-specified procedure helps a lot, especially for countdown. If we just use the GPT-4o to solve the countdown task, the 8% accuracy. But if you tell the model how to solve this task by doing this depth-first search, it can actually give you a 67% accuracy, much higher. Travel planning is a harder task. So next, I want to show you something actually really interesting to me is that this actually, we did put this result in the paper. So we recently tested the R1 models, the R1 distilled models. We want to understand if the models have been already trained with the reasoning or long chain of thought, but the model still needs this kind of pre-specified procedure. So here are the results. Here are the results on countdown. So they're actually bottom result numbers here. So basically, we consider like a 4 reasoning models. So basically, all the distilled models of this distilled model from the R1 model, and also this S1 model from Stanford, which actually also built on the Chen 132 billion model. And what we found here is, so first, for the base model, that basically the instruct model, the blue bars here in this figure, if we don't give the models any procedure, basically they cannot solve anything. But if you give the models the procedure, the model is actually able to achieve pretty good performance, especially for the larger models. And for the reasoning models, that is the green bar here. If we don't give the model basically the procedure to execute, the model can do actually pretty good, well, like to come up is actually search procedure to solve this problem. But if we actually give the reasoning model still the pre-specified the procedure, like reasoning models plus the LongProc chain of thought, we found that actually the yellow bars are still better than basically the green bars here. That means that the reasoning models still benefit from this kind of pre-specified task-specific procedure, but still the reasoning models are already very capable of coming up their own procedures to solve like this task like countdown and the travel planning. Okay, so I'll just pause here a little bit and see if there are any questions before the next I'm going to talk about how to build a long context model. Yeah.
Any questions? So I want to ask that so long context and the long generation kind of have some correlation, right? So when you try to generate something very long, you need to process your long history of generation. So do you find any like a correlation between like model performance in these two benchmarks?
Oh, right. Yeah, I would say like okay, first, there are definitely a lot of correlation. That's a good question. I don't think we even put them together, but that's a really good question. So first, I want to emphasize that for the LongProc task, the input usually actually not so long. It's more about the output length. But for the helmet task, because the input length is actually very long, so it actually requires more about the recall ability to actually retrieve the relevant information from the long input. But yeah, I would say definitely correlation between the two, because the model has to process the input to actually do the good long form generation. Yes.
Any other questions? So I'll go ahead with maybe philosophical questions a little bit. What do you think that we should expect large language models to do? So for example, countdown, do you think that countdown is something that we should expect LLMs to do?
Why not? We want the model to solve. The question is how many people care about countdown task. But right now we want the model to solve like Olympiad level, like mathematical problems or the competitive programming problems, because they actually really require like a lot of the complex like reasoning to actually solve these problems, right? Countdown is just like a demonstration of a very easy problem solving process using just a search that you can actually do this task. I think it's a good benchmark to evaluate, but the question is whether it's practical or how many people actually care about it. Yeah.
Yeah, I think there's also another school of thought that we should, maybe we can rely on a bunch of tools to do a lot of tasks for us, including mathematical reasonings. So we should not, we may not need LLMs to do everything for us. If they just know what tools to call with what parameters, that should be enough. And that is just maybe two different school of thoughts. I'm not sure which one.
Yeah, I agree.
Wanted to know your thoughts about what is an ideal LLM that we are envisioning in the future?
Yeah, there is definitely. Actually, this is a very good question to leave at the end. Maybe I think I should move on. Yeah, but yeah, can I leave that to the end, because I think that's really the argument between, let's say, long context models or whether we even need a retrieval or this kind of tool use. Yeah.
Absolutely.
Because I still have like a really big part of how to build models.
Sure. And there is one question on the chat, so I'll read it loud. It says, from Yashin Zhu, the question is, what are the differences in evaluation focus between long procedural tasks and general reasoning tasks? For example, are they controlled to be longer or other metrics are included?
The control to be longer? Sorry, I'm not sure if I understand. I'll just say, like right now, a lot of reasoning models focus on, let's say, solving mathematical problems or coding problems. They will not give the model what the procedure to follow. So they ask the model to come up with a solution, the procedure to think about how to solve this problem, and then reach the final answer. But the one thing about this LongProc is we actually specify the procedure. We want the model to actually be able to do the instruction following actually to reach the final answer. So it's more about like checking the model's ability to actually follow the procedure and then do the step-by-step generation. But for most of the reasoning problems, they only give the input and you need to figure out the procedure. I hope that answers the question. Yeah.
Okay, thank you.
Yeah.
If you did not get your answer, so please ask your question again at the end by unmuting yourself. Okay, you can.
That's good. I think I have only 15 minutes left, so I want to just move on and finish this part. I'm really excited about this part. Probably I will have to go quicker about this part. Okay, the last part I want to talk about is actually finally we developed all these benchmarks and we wanted to finally train our own models. So the last part I want to talk about is actually a family of models we actually developed at Princeton called ProLong. So it's actually a family of the state-of-the-art under 10 billion size model, open source, and they can support up to 12,000 context lengths. So we wrote a paper about this. The paper is called How to Train Long Context Language Models Effectively, and led by my student Tianyu and Alex. I just want to mention ProLong is actually stands for Princeton Long Context Models. Okay, so what exactly is ProLong? It has a lot of engineer efforts, but we actually learned a lot along the way and learned a lot of really interesting things. I'll just first tell you how we actually produce this ProLong model. So the ProLong model, we started from last summer. And then we start from the Llama 3 80 billion model. At that time, 3.1 was not out yet. And that model has a context length of 8,000 tokens. And then we did a continued pre-training on this on top of the Llama 3 80 billion model, on a mix of the high quality long context and short context tokens. We have used actually 40 billion tokens to actually do the continued pre-training stage, and which eventually expand the context window to actually 12,000 tokens. And we have also a very brief supervised fine-tuning stage. Here, we only use the short context instruction tuning data. And we found that actually ProLong achieves a very strong performance, actually among the sub 10 billion model size on the helmet evaluation, but also on actually many other benchmarks that we tested. Very interesting, after when we were basically about to wrap up our project, the Llama 3.1 actually came out. And the Llama 3.1 actually was trained on 800 billion tokens. So we actually only used 5% of the training tokens compared to Llama 3.1. So that means that we actually definitely did something really interesting to think about how to really make it work. So here are just quick results. So the bunch of models are actually around 10 billion size models. And so the green row here is basically Llama 3.1. And this is our ProLong model based on Llama 3 model. And we actually found again, we only use 5% of the compute, and we actually achieve better performance on most categories, except for the summarization, we are actually behind. But all other categories, we're actually good. Okay, so before I talk about what we learned from the ProLong, I want to be very quick about this has actually taken us a very long time to actually really finally figure out how to actually develop this ProLong model. So the key question here is, if we have a pre-trained language model with a shorter context length, how can we actually extend the context length of these models effectively? So actually a lot of the really research question we can ask in space, whether we actually want to do training or not training. If we were actually going to do the training, what data we actually want to train to actually ensure that like a diverse downstream applications such as RAG. And another question is actually really underexplored question is, how should we do instruction tuning? And there has been also a lot of work in our community trying to explore the efficient architectures for long context models. So how can we actually really make models to actually become more and more efficient to actually handle the long context? Even in my group, before we did the ProLong, we had actually 2 papers, one in EMLP 2023 called auto compressors, and another paper called SEP in ACL 2024. We basically tried to modify the model architectures, transformer model architecture, to make sure that hopefully these models can actually incorporate the long context in actually more efficient ways. But we actually turns out this type of efficient architecture don't work as well as we expected. There are actually a couple of things we actually learned here. The first thing I actually already touched, basically like for most of this talk, is that when we were developing these models, we actually found that how to evaluate and compare the different design choices is actually really a painful thing. That actually really, because we don't have a reliable evaluation metrics, that really makes a lot of the like efficient model architecture or the context expansion techniques to be actually not clear why they're actually useful, because a lot of work actually just focus too much on perplexity or needle in haystack. That's actually the reason why we actually decided to develop the helmet as actually at the same time. And also, it's really big bitter lesson here is we found the efficient model architectures actually just not as effective as actually as a full attention models. And thanks to a lot of the hardware like optimization, is actually pretty efficient to fine-tune long context models with full attention. Just give you one example here. If you want to fine-tune an 8 billion model on the 12,000 context length, it's actually pretty doable. It's actually a very big context length. It's 12,000 context length. It's actually very doable to do this on 8 A100 GPUs. So it's still a lot of GPU memory, but it's actually much doable than we actually previously thought. And at this point, we actually also start to realize the importance in developing in the long context models is actually not in the model architecture, but it's actually on the high quality data, especially the high quality long context data. And the last year, there was a very nice paper called Data Engineering for Scaling Language Models. So that really basically addresses the exact point that data engineering could actually play a more important role than the model architecture. Okay, so next I would like to tell you basically some key findings we learned from developing ProLong. Just for the sake of time, I probably have to go really fast and just tell you some of the main results here. So the first thing, the first aspect I want to talk about is evaluation. As I already mentioned, we actually really, when we develop models, we should really look at downstream tasks instead of the needle in haystack or the perplexity. And another thing we actually found really interesting here is, even if we want to do a lot of the ablations or design, the model design choices for the base models, for the continual pre-training stage, we actually have to evaluate these design choices after the supervised fine-tuning. As you can see from the curves I showed here, if we don't do the supervised fine-tuning, just a lot of the trends will actually just not clear if you don't do supervised fine-tuning. So you can see a clear upward trend when you throw in more data after you do the supervised fine-tuning, as the orange curves show here. And for some tasks like question answering and summarization, if you don't do supervised fine-tuning, basically the performance is just very bad, and it's actually not just really informative to actually help us make any design choices. And another point here, the important point here is that it's actually also very important to check whether the short context performance is actually preserved or not. Actually, a lot of the existing long context models, they just care about the perplexity or some long context task, but they actually don't really check that it's actually very easy to lose the performance on the short context tasks such as MLU or health work and so on. Okay, so the next point I want to talk about is actually data engineering. As I said, data engineering is actually very important for developing long context models. And how can we actually get the high quality long context data is actually really the key in developing the long context models. So first we look at the long context data mix. So we actually try to figure out what are the resources we can find from, for example, the pre-training corpus like Slim Pajama for the a natural source that have at least 128,000 tokens or 512,000 tokens. And then we studied a lot of different sources. And then we finally found the books and code actually probably the most important sources to actually train the long context models. And then we did a basic 1-to-1 ratio by combining the books and real codes data. And another probably a bit counterintuitive thing we found is actually the high quality of the short context data is also actually very important for the long context task performance. So we actually did ablation studies on a bunch of the short context data like Slim Pajama, FanWeb, DCLM. But eventually, we actually proposed our own short context mix. We found that actually the quality of the short context task matters in the short context task, but also matters a lot in the long context task performance. As you can see, there's a pretty big improvement here if we do the short context data mix correctly. Finally, this is also very important. If we really want to train long context models, you actually need to mix long context data and also short context data properly. And eventually, we actually mix the long context data 60% and with 40% short context data. And then we found that if you actually just train on the long context data, this actually hurts the performance on the long context task. This is actually very interesting. If you use a lot of long context data, it definitely hurts the performance in the short context task. But it actually also hurts the performance in the long context task. So that's why we decided to use the 60% of the long context data and the 40% of the short context data. And the next, I want to talk about a little bit of scaling. So as I said, we used 40 billion tokens to train these long context models. And we actually did 2 stages of training. So first stage, we trained on the 20 billion tokens with documents up to 64,000 lengths. And the second stage, we trained on 20 billion tokens with up to 512,000 token lengths. That's actually a surprising finding here is we found that if we train on the data context length that actually longer or beyond the evaluation length, this can give us actually additional benefits. So just give you some idea here. So after the first stage of training, and then we switch to training on the documents that have a context length of 512,000 tokens. And then we still evaluate on 64,000 tokens, or even shorter, 32,000 tokens. We still also observe like even significant improvements or even bigger gains. So this is a control study. If you continue training on 64,000 tokens versus training on 12,000 tokens training, we actually found that training on the longer documents would actually give you benefits and also bigger gains compared to training on the short 64,000 documents. So this is actually a very interesting finding we found in this paper. Okay, so the last thing I want to talk about is actually supervised fine-tuning. So I will just not talk too much here. Basically, like we tried right now people think a lot about the synthetic data generation. So we also thought a lot about how to generate the long context instruction tuning data for the instruction tuning. But we also evaluate on like different types of the short context instruction tuning data. The surprising result we found here is we don't find actually adding any synthetic long context data actually helps at all in any of our experiments. So at the end, we decide to just do the instruction tuning on the short context data. So we actually use the Archer chat as our kind of data set that we actually used in the instruction tuning data. I think this is still like an open question in the field. So there are still a lot of things we can actually start to think about how to do the long context instruction tuning data, because we just don't have like a high quality source of such data. So in the paper, we basically like present like a complete recipe for developing such long context models. So in the paper, we also have like detailed discussion of how to do the row-based frequency and how to do the document masking if you do this kind of continual pre-training stage. Okay, so this is basically all I want to tell you about ProLong. I know I went through this part really fast, but I'm happy to take questions if we have time at the end. At the end of this talk, I just want to basically in this talk, I talk about both the benchmarks and also how to develop long context models. So at the end, I just want to talk about a bunch of the open research questions in this space that I have been really thinking a lot recently. So the first question I just already talked about is we actually don't really have high quality, long context instruction tuning data. So how should we actually synthetically generate high quality long context instruction tuning data? I think I have seen some of the follow-up works in this space, but I still don't see there is like a really satisfying solution to this question yet. Second question I've been seeing a lot recently, really very recently, is these days people all talk about reasoning models. So we know that we actually need long context models for solving the reasoning task. But the opposite question is, if we can do this kind of RL training or this R1 style training, does this kind of training actually give us the long context abilities of such models for free or in some ways? That's actually a really interesting question to think about. Finally, I want to talk about this kind of RAG point. So we know the RAG needs long context model to support. But can we actually, there has been a lot of discussion about whether we can actually use long context model to replace RAG or not. So I just want to talk about, I don't have time to talk about this, another CIIR paper we did this year. So we call this knowledge intensive retrieval. So we basically collected a bunch of really hard questions from the coding, from the coding domains, mathematics, and the stacks change in biology and economics. And then we collect a bunch of relevant documents that the human annotators believe that those documents actually are relevant to the query. And they actually really require some in-depth reasoning to actually help solve these queries. But we did a lot of tests. We found that the current long context models are still not really able to leverage this kind of knowledge-intensive type of the relevant context actually well directly in this long context documents. So that means that we are still not solved yet with the long context models. All right, so I know I rushed quite a bit. So basically in this talk, I talk about these projects, about how to evaluate long context models and how to develop long context models. And I'm happy to take more questions. Yeah, thank you so much.
Thank you so much. We are technically over time, but I think we can get one question if there is any. Otherwise, we can. Okay, so there is one question in the chat, Deepak. Deepak, would you like to unmute yourself so you probably can ask the question better?
Yeah, I think thank you for the talk, first of all. I was just curious about other effects. Like when you have long context, you have all these, you have positional information or where the information is located in this giant context, and also maybe the local context around the information matters as well. I mean, so when you benchmark all of this, how do you sort of, the whole benchmarking space sort of explodes once you start looking at all these little things that can happen. So I'm just curious if these matter and whether the benchmarks have to eventually sort of actually take into account these kinds of effects.
I'm not sure if I understand the question precisely. You are talking about how the impact the position of the relevant information, key information, affect the performance. Is that
That's
right?
right. In these long contexts, position and the local context around the information, how that impacts performance.
Yeah, right. So a couple of years ago, there's a really famous paper called "Lost in the Middle." It basically tries to say that in this RAG setting, open domain question answering, if you put the relevant documents at different positions, it actually gives you like a basically lost in the middle, like a curve, right? So basically, the performance is worst in the middle. So I wouldn't say the problem is solved. Yeah, so that's why the needle in haystack is a synthetic task that actually evaluates whether there is something missing in the middle. But at least in our benchmarks, so for all these benchmarks, we can actually control where the relevant information is. For example, the RAG or citation, we are actually able to basically either shuffle the documents or like randomly place where the key information is. So we actually did a lot of control there to actually ensure the output will not be like biased to like particular positions. Yeah. But I agree there are a lot of detailed things we can think about there. Yeah, the internal designs. Yeah.
Thank you.
Okay, thank you so much. Let's thanks Danqi one last time.